Hello and welcome all of you to Easy Electrical. As you all know that we are running our electrical measurement subject, the basics of measurement system, that is our unit 1, and we are now into our fifth lectures. That is, we have earlier covered 4 lectures, and now we are taking up the damping torque. Now I would request all of you to first go through all the 4 lectures and watch this lecture, as this is a part of the series. Now coming to today's class, uh, as you all know that to give you a small idea about Easy Electrical, it is a online only coaching institute where we are basically guiding the students to reach their dream government job. Basically, we are providing the coaching for the SSC JEE 2021. So if you have any questions regarding SSC JEE preparation, you can call this number 833506 7725, and you can know whatever the class schedules are there. Now coming to the next part, that is, in the course what you will get, you will basically get a concept based module where you will get the technical part, you will also get the non-technical, and after the classes you will get the notes. And for every month we basically conduct a test series, a monthly test, and practice questions are given after every class. One of the important features that we have introduced here is, well, that whenever you take a class for Easy Electrical, that class will be recorded and it will be uploaded to YouTube, and it will be available for you uh, for the whole lifetime. Okay, now coming to today's class. So today I'll be taking care of the uh, damping torque portion, and now we have studied up to the indicating instruments, deflecting torque, controlling torque, and damping system. So from the beginning we have seen that the deflecting torque TD is proportional to I in some instruments, and in some instruments we have observed that TD is proportional to I square. In the earlier class we have also seen the details of the control torque. For control torque we have seen is proportional to theta, that is the deflection, and in some cases we have seen that control torque to be proportional to sine of theta. To give you a small idea that for spring control instruments we have basically seen this phenomena, and for gravity control instruments we have basically seen this phenomena. And in the case of this approach, proportionality approach, we have seen in PMMC type instrument, to give you a simple idea, and in MI type instrument we have seen this. So whenever we will be taking care of the in details constructions and details of the PMMC and MI type instrument, you will have a better idea of this, how it is coming out. Now when I am discussing the damping system, basically damping systems are classified into 3 types, 3 to 4 types we can say largely. One is what we call it as air friction damping, and second is we call it as the liquid friction damping, and third we call it as the eddy current damping. Third we call it as the eddy current damping, eddy current damping. And another point is that is electromagnetic damping, that is similar to eddy current. Electromagnetic is also there. Electromagnetic is also there. There's another classification is also there. Now in the damping system, what we have observed here is that the damping torque is basically proportional to the rate of change of deflection with respect to time. Now this phenomena is basically what we call it as omega, or angular velocity. So T damping is coming out to be proportional to omega, and if we replace this proportionality sign, we will write a constant term, say k damp we are using, suppose, and omega. So this is the representation of the damping system and how the torque is varying with respect to the deflection. Now coming to our next topic, that is indicating instruments damping torque. We have classified that air friction, fluid friction, eddy current, and electromagnetic. Now to give you some idea about the examples, air friction damping is basically employed for whenever we are finding this MI type instrument and electromagnetic type instrument. Fluid friction damping is basically employed for the electrostatic voltmeters, whatever the panel mounted meters and wall mounted meters are there. We are basically using the fluid friction. Generally, eddy current damping is used for the PMMC and the induction type instruments. And electromagnetic is basically galvanometers and flux meters we are basically using. So in certain examinations they ask this type of question that in MI type instrument what type of damping you see, and in electrostatic voltmeter or wall mounted panel mounted type instrument what type of fluid friction damping you see. So these are the short questions that basically asked in SSC JEE examinations. So we are basically taking care of that part only. Okay, now coming to the today's topic, that is to give you a small idea about what is air friction damping. Basically, air friction damping is seen as you have seen earlier in MI type instrument. Okay, so MI type instrument, of when I will classify, you will get the idea that there are two types of MI type instrument. One is called as the attraction type instrument, another is called as the repulsion type instrument. So in the next I will discuss how the attraction type air friction damping is employed. This is basically an example of a attraction type air friction damping is employed basically in this case. Here you can see the pointer is there. This is the pointer. Here you can get the idea that here it is a pointer. This is our pointer. Now when this pointer is moving, if suppose it is moving in this direction, if it is moving in this direction, then from this arrangement you can see that the piston will move in this direction. So there will be an automatic air friction that will act on the pointer, and the damping is provided based on this air friction. Here also this is the second arrangement. In the second arrangement you can see the pointer will be, suppose here somewhere here will be the pointer arrangement, and the vane, that is a, here basically you can see a metal strip may be placed, and this metal strip basically moves as per the movement of the pointer. Suppose the pointer is moving in this direction, so in that case the vanes moves in this direction. So you are getting that idea, simple idea. Here you can see the same thing is drawn here. There is an air chamber is there. In the air chamber, this piston basically moves upwards or downwards based on the direction of the pointer. Here also you have seen the control spring is shown, the vanes are shown, the pointers are shown. Some simple figure is drawn here so that you can get the idea of the air friction damping. So basically what is happening here is the air friction is acting as a damping source. Basically what is happening here, the air friction is providing us the damping, the damping. Air friction is providing us the damping. Okay. So this is the common example and very easy example. It is very cheap as well. The cost of it is also very less. Now coming to our next part, that is in our damping system, I will be giving a small idea again about our. See here also I have marked the air attraction type instrument. This is a moving iron instrument. This is the iron. This is the iron portion you can see. As the pointer is moving, as the pointer moves, the iron moves, and this piston also moves through the air chamber. Here you can see a simple connection diagram is shown. The moving iron type ammeter. This is the terminals I have marked, and here you can see the dashpot is present. Air dashpot. Inside this air dashpot or the damping vane, you can see here inside this air dashpot. Basically, this piston actually moves, and by moving, the damping is provided in the pointer itself. Here you can see the hairspring arrangement, the geo adjuster. Okay, all the arrangements are shown here. This is the moving iron. Here you can see the picture here. Here you can see the actual figure of the moving iron. This is the actual moving iron. You can see here. Okay, so this is the typical understanding of the air friction damping and how it works. Now coming to our next system, that is our fluid friction damping. Now you can see here basically a liquid is used. Okay, so in the liquid there is a vane which is getting rotated, and this up to this vane there is an pointer is also connected in this case. So as the vane rotates with respect to the pointer, we can see that there is a friction that is working in the system. So based on that we can see the damping is provided. So when we see the vein moving in the liquid, provides for the damping in the pointer. Okay. Now one more thing here comes in view, that is, as there is a liquid, this liquid has some properties. So properties of the liquid, that must be, we must properties of the fluid or the liquid. Okay. So what are the properties of the fluid? First of all, there has to be no reaction, no reaction, no reaction between the between the between the vein and the fluid, and the fluid. No reaction must take place. Number two, the liquid should not evaporate. The liquid should not evaporate. Should not evaporate. What will happen if it evaporates? If it evaporates, then the quantity of the fluid will reduce. If the quantity of the fluid will liquid will reduce, what will happen? The friction will get reduced. Now, number three is that the viscosity should remain constant. The viscosity of the liquid should not vary with temperature. With temperature. So the viscosity of the fluid should not vary with temperature. This is one of the most important points. And one more thing is that it should be a good insulator. It should be a good insulator. It should be a good insulator. Good insulator. So these four are the typical or the main properties that are there, that has to be carried by the oil, whatever we are using, whatever the fluids we are using for the rotation of the vein inside that. Okay, so you can get the idea of the fluid friction damping. Now coming to the next system, that is the eddy current damping. First of all, we need to understand one simple point about the eddy current. Okay, so what is an eddy current? Eddy current is basically, suppose we are having a north pole and south pole like this is placed, and we are having a metal former, and which is moved in a magnetic field. Whenever we move a magnetic field, here you can see in the surface of the body, this is the surface, this portion is basically the surface of the body. In the surface of the body, this former, in the surface of the body, there is a formation of the circular currents. Circular currents are formed everywhere there is circular currents that are formed. Okay, so these circular currents are nothing but what we call it as the eddy currents, and these eddy currents are used to damp out the system oscillations. In that case, this type of damping we call it basically as a eddy current damping. Now to give you a small idea, this is the typical arrangement of a eddy current damping. Here you can see the pointer, here you can see the disc which is getting rotated, and this is the damping magnet that we are using. Basically the disc actually rotates with respect to the current flow. Whatever the current is going, based on that the disc rotation is basically done, and the disc rotation determines the pointer. Now as the disc rotates, the final damping is provided by this magnet. Now how it is providing the damping? Basically in this manner. In this manner means when the disc rotates, this fixed permanent, there is a basically permanent magnet. Okay, this permanent magnet basically provides for the flux. As the disc rotates, there is a eddy current getting introduced, or the eddy current is getting formed. Now this eddy currents, in response to this permanent magnet, will produce another flux and will oppose the flux which is coming from the permanent magnet. So in this way, there is an opposing force which is acting on the disc. That is, this opposing force actually acts in the reverse direction of rotation of the disc. As the reverse direction of rotation of the disc, this thing happens, it provides a natural damping or natural damping protection to the oscillation to the damping for the pointer. Now in this way you can get a small idea about the damping, and that is the eddy current damping. Now here we have represented the eddy current damping figure. Now basically, to give you a small idea, there are two main fundamentals are there. One is we can use a metal former. There are two options. One is a metal former, in which we can find we can use the eddy current damping, as well as a thin aluminum disc, a thin aluminum disc. These two are the basic necessaries. Onto which the eddy current damping can be employed. Now we basically both the cases we basically reach at a conclusion that T damp is equals to some constant Kd into omega here as well, and T damp uh, equals to Kd into omega here as well. But the constants vary for the metal former, and here also the constants basically vary. Generally in SSC JE level, these questions are basically not asked about what are the values of the Kd. Just to give you a small idea, I'll be writing the expression of Kd. For the metal former, the Kd expression is basically Kd is basically B square L square B square L square D square B square L square D square BT B square L square D square BT divided by BT divided by 2 rho 2 rho L plus D, 2 rho L plus D. This is the representation, where you can see the B is the strength of the magnetic field, omega is the angular speed, L is the length of the former, T is the thickness of the former, B is the width of the former, D is the breadth of the former, and rho is the resistivity of the material of the former. These are the basic examples. No need to remember all these things, because these questions are generally not asked. You just go through this. You can find it in any textbook as well. For this thing, the value is basically b square r square dbt. Here it is b square, here it is r square dbt divided by k into k into rho. Okay, so here B is basically, you all know, the flux density, T is the thickness, B is the width of the permanent magnet, D is the depth of the permanent magnet, rho is the resistivity of the material, and omega is the angular speed. Here one more thing you must know, that is the K. K is basically a factor which is taken into account for the whole of the system. That means here if you see, if I consider this whole whole disk, what will happen is, not only the eddy current is produced here only, throughout the system, throughout the disk there will be eddy currents formed. So to take care the whole of the disk, this factor K is taken into consideration. The factor K is taken into consideration for taking in the eddy currents. That means, suppose this is the disk, and here I have seen the eddy current is getting formed. Not only this portion, here also will be eddy current formed, here also will be eddy current formed, here also will be eddy current formed. So to take care all this K factor is basically coming out. Actually we don't need that much mathematics, only this much will be sufficient for the for us. Now this is another figure, of the eddy current damping. Here you can see the magnet is placed. This is the typical presentation of the magnet, where the magnets are placed. This is the bar magnet, this is the disc. Actually what I was saying, that here there will be eddy currents are induced, here also there will be eddy currents, here also there will be eddy currents, not only in this portion but also throughout the disc. That was the factor. That's why we are using the k values. Okay, so here basically simple machine is shown, simple instruments is shown, where the eddy current damping is used. Okay, now the last topic is our electromagnetic damping. You can see here the two poles are there, and the two poles are actually injecting this eddy currents in the disc, and this way the damping is getting formed. So here electromagnetic damping, some details I have provided. A thin disc of or vein of the conducting but non-magnetic material like copper or aluminium is mounted on the spindle carrying the moving system of the pointer. Basically, in case of the galvanometers, whatever we are there, then there was flux meters are also there. In galvanometers and flux meters, we basically employ this method. Okay, just these 2 points you need to take in mind. Another 3 points are noted here. First of all, the disc or the vane is positioned so that the edges rotate between the poles of the permanent magnet, as you can see. Damping torque decreases with the movement of the magnet towards the edge of the disc and becomes zero. In induction type instrument, by placing a damping magnet the opposite side of the disc from the electromagnet, so the disc serves the damping as well as the operation purpose. Both the purposes can be served. Basically these type of instruments, as I've already marked, as used as a galvanometer and as a flux meter. Galvanometer is basically one such device which basically measures the deflection only. Whether there is a voltage is there, whether there is a current is there, only deflections will show, not the actual value we can get. Now coming to us the next topic, that is in our air friction damping, what all are the advantages? Now first of all, air friction damping, we know that it is a cheap, so the cost of system will be very much less. Now coming to the next property, that is it does not require any permanent magnet whose introduction may lead to the distortion of the operating field. Now one thing we must know, that in air friction damping, wherever we are using the air friction damping, basically in mi type instrument we are using, we are basically using a soft iron, and this soft iron basically leads to weak magnets. Okay, so weak magnetic field is produced basically in mi type instrument. So whenever there is a weak magnet is introduced, weak magnet is produced, basically there is no such a thing as the distortion of the field is present. Now this is a plus point. Here also it can be treated as a minus point as well. Okay, first of all, what we can say that if the piston is there, we have seen the piston is there, if it is bent in any way, then there will be a frictional error. Okay, other than anything, the frictional error will be there. Not only the air friction, the resistance in the vane may be present. That resistance in the vane may be physical as well. That is, the outer walls may be touching the vane. That will create a huge nuances, and the result will be errorous. Error will be there in the result. So as I have already said, that a weak magnet is produced. This weak magnet is basically an error as well. Okay, because suppose in a mi type instrument, if I inject or place any heavy high magnet near to mi type instrument, what it will show, it will get distracted by the strong magnetic field, and this strong magnetic field will change the value, will change the actual reading of the mi type instrument. So that is one of the most uh, uh, faults that we can see, or most difficulties that we are finding in mi type instrument. Now coming to the next topic, that is our fluid friction damping. In fluid friction damping, what are the advantages? First of all, the oil is used as an insulation. Second is the clearance, that there is a small clearance required to keep the damping, because the fluid is actually working as a insulation. Now coming to the disadvantage, first of all we need to keep in mind that the oil must be put in a vertical position like this. So the placement of the instrument must be also in a vertical position. There is another issue of the oil creeping through the instrument. Oil generally creeps out, and because of that the instruments become dirty. One advantage we can add here as well, due to the upthrust of the load on the bearings, it is reduced, thus the reducing of the frictional error. Okay, so due to the upthrust means the whatever the liquids are there providing the upthrust to the moving vane, it will reduce the frictional error. Okay, it will not increase the frictional error, rather than it will reduce the frictional error. Now coming to the next part, that is the eddy current damping. Whatever advantage, we are basically seeing the advantages only. Some disadvantage we will know. It is the most effective method and the best method, we can say. Another form is that the convenient. It is very much convenient to use the instrument where a metallic disc and a permanent magnet are already a part of the system. One disadvantage we can say that whenever we are using the metal disc or the metal former, the eddy currents flows or setup. Okay, so this will cause erroneous readings as well. Okay, so this is one of the problems that we can see. Okay, so in metal discs, if it is placed, the eddy current flow or it will start to set up. So here key points. What are the key points we must remember? First of all, the first thing that we must know, that what is the most effective method. The most effective is eddy current. Okay, the eddy current damping is the most effective damping. Then we can say that fluid friction is the next most effective, fluid friction. And the last one is the air friction. In this way we can say that the order of effectiveness, this is the order of effectiveness, order of effectiveness order of effectiveness. Another arrangement or another order is there, that is how we can say the priority. We are basically priority wise, if we see that eddy current has the fast priority. Whenever there is a possibility, we can use the eddy current. Then there is air friction, and whenever there is no such option is there, so we use the fluid friction. So this is the priority, fluid friction is present. So this is based on priority. This is based on priority. So these 2 points we can generally keep in mind, that what are the key points for the damping system. So damping system, one important point I had already earlier discussed about it, and that is, if it in this direction, if we put the theta, and if it in this direction, if we put the time. So generally, one system we will find that if this is, suppose the final deflection position is there, okay, for overload or over damping situation, something like this curve are obtaining. Suppose in certain cases we have obtained something like this curve, and in certain cases we have obtained like something this curve we have obtained. Okay, so continuously changing curve we have obtained. So these are the 3 curves we have obtained, and from these 3 curves, what we can consider, there will be giving you this curve and saying what all they represent. So you can correctly say that this is an overdamped system. This is an overdamped system. This is a critically damped system. Critically damped system. Okay, and this is a underdamped system. Underdamped system. Underdamped system. So what do you mean? What do we mean by critically damped, overdamped, and underdamped? Suppose I am giving a supply to a ammeter. Initially, it is showing 0 ampere. Now, when I have given the 5 ampere, suppose supply 5 ampere current is flowing to the ammeter, it takes a longer time to reach a value of 5 ampere. If it is taking a longer time, then we can say it is a overdamped system. Suppose it is reaching the value at a very fast time, that is quickly it is reaching the 5 ampere value, then it is called as a critical damp. Now one more thing is that if the pointer moves in this fashion, that is slightly reaching the value of the 5 ampere, that means that the pointer is moving in this way. First it is here, then it is there, then it is continuously increasing, decreasing, and ultimately it is decreasing, showing us the 5 ampere value. So in this way, if the pointer is moving, that means there is a continuous oscillations, and after that it is reaching 5 ampere. In that case, we are using the underdamped system. One point I have mentioned here as well, that is the underdamped systems we are basically preferring. Why we are basically preferring here is because pointer has some mass, and it produces inertia, and due to that inertia, whenever we are using the critical damping, it is not good for the mechanical system, and under damping is preferred, so that the inertia gets died out in the under damping state. So that is the reason why we are using under damping. Another point we must remember, that is, if suppose there is no damping is provided, so what will happen is, as there is no damping here, the oscillations will continue like this. It will never come to a steady state. So this will be present. Okay, this is an undamped situation. This is the undamped situation. Undamped situation, you all know, undamped situation. So you just revise all the things that I have taught. Thank you everyone for listening to our class, so up to this point. Now one more thing I need to add, that is, if you have any doubts regarding this class, you can mail me at electrical easy gmail.com, or use WhatsApp, and you can send me your messages or queries at 8335067725. Thank you everyone for listening to this class, and hope you are revising every topic. Just go through one by one, you will have the total idea. Thank you everyone.